Welcome to today's session as a part of Cybersecurity Awareness Month at Digital Research Alliance of Canada. I'm Ralph Rochjavan, and I'll be the facilitator for today's session, High Performance Computing Infrastructure and Zero Trust Architecture. Cybersecurity threats become more sophisticated, and the traditional castle and moat security model is no longer sufficient, especially in the complex environment of the high performance computing. That's why I'm very excited about today's talk, and we will learn more about the Zero Trust Security model in HPC. I'd like to share a few words with you before starting the presentation. As we proceed with our session today, we acknowledge the First Nation, Inuit, Métis nations, and communities who have been harmed by the colonial and unethical research practices. We also recognize the importance of their data sovereignty and research priorities. On behalf of the Digital Research Alliance of Canada, we commit to understanding and embracing our role in reducing harm and advancing reconciliation in research. The Alliance seeks to provide a welcoming, engaging, and safe community for everyone. Discriminatory language is not appropriate in any venue or platform. The Alliance does not tolerate harassment in any form. Harassment is understood as any behavior that threatens another person or group or produces an unsafe environment. Now it's my pleasure to introduce our presenters for today, Tyson McCauley from the National Center of Critical Infrastructure Protection, Security and Resilience, and Daksha Bhaskar from Microsoft. Tyson is a cybersecurity and networking researcher and executive with 25 plus years of experience, specializing in HPC, enterprise and critical infrastructure system. His background includes leadership roles at startups and enterprises such as BAE Systems, Intel, Fortinet, and Bell Canada. He is the published author and the research affiliated with the Carleton University, active in the security standards through NIST and ISO. Tyson is the founder of the boutique security firm called Inframetric Analytics. Daksha is a principal security architect at Microsoft. She has over 25 to 20 years of experience in the telecommunication service provider industry, specializing in system security development for complex solution architectures of carrier grade. She's passionate about the security and emerging technology, engaging with the broader security industry to improve the state of the security architecture of technology. So without further ado, I hand it over to our presenters, Tyson and Daksha.
So without any further ado, Daksha, would you like to introduce yourself further or just say hello and I'll take it away?
I'll just say hello. Ralph gave us a great introduction there. Thank you. So we'll excited for the talk and look forward to the next hour, spending the next hour with everyone.
Absolutely. And I recognize a number of names in the participant list, so it's good to reconnect with all of you. It's probably been a year or two. But as you can see, I've been pretty active in this area. And just to restate what Ralph said, this is a white paper, actually. This presentation is based on a white paper, which was just released today. It's available through the Carleton website and the Pulse and Practice Journal, but I've also embedded copies of the paper here. Last time we tested, the links worked. The paper is broken up into two phases, the main body, and then a larger annex, which has got detailed controls on the zero trust maturity model. And the way we came across this information was a combination of Daksha and I both participating in standards research. We participated in the NIST High Performance Computing Security Working Group. In fact, we're presenting this to them next week. And we did specific formatted interviews with HPC cluster managers in Canada and the US and with HPC vendors to come up with this information. So some of the characteristics of HPCI, so in this case, we're talking about the infrastructure, really not focused on the software itself. And of course, characterized by large data sets and therefore big storage area networks, parallel processing across servers and within chassis, which drives the need for high performance networking, high performance systems themselves with very expensive GPUs and the best of the enterprise processors. And then all of this coming together into a very powerful cluster type configuration that is different from what we would see in an enterprise. And in the paper, we actually do side-by-side comparison of HPC versus enterprise. And certainly one of the conclusions we reach is that in a typical enterprise system, they can do things, such as easy scaling and bolting on commodity hardware in standardized configurations, and it will just run. In an HPC environment, these tend to be more fragile. The configurations are often tuned very carefully to the hardware and the number of hardware elements in place. So we see differences there for sure. We also see that HPCI is probably obtaining the status of critical infrastructure. And if you look at Canada has got 10 critical infrastructures, and it is not at this time calling research infrastructure or HPCI critical. In fact, they don't even have industry definitions for any of these critical infrastructure sectors. Canada's got a number of gaps, starting at the policy level. However, in some of our allied partners, for instance, in the case of the United States, they define critical infrastructures with 16 sectors. Data centers are included within the definition for communications. And in the case of their government sector, they actually explicitly call out research facilities and infrastructure. In the case of Australia, two interesting things is they certainly call out data centers and the infrastructure inside as critical, and they specifically call out education and research infrastructure. All of this is indicating that the investments being made in HPCI reflect priorities in both national security and prosperity. And part of the objective of this paper and this work is to act as a source of opinion and insight to the policymakers around the value of this infrastructure, why we need to be focused on protecting it, and also, of course, to provide some support to the actual HPC managers in this country. Some of the attacks that we've seen on HPCI, one of my favorite ones, maybe not HPCI, but it was so early, I thought it's worth mentioning. Back in 2016, you may recall that one of the first instances of AI to try and go mainstream was the Microsoft Tay chatbot. And within 2 days, internet trolls had turned it into what the BBC called was a sex-crazed racist. So that was a good example of how large applications can be rapidly degraded if they're not properly protected. Now, in that case, that wasn't so much a cybersecurity issue as just a wanton behavior on the internet community's part. But now we know never do that again. But more recently, starting in 2020, we started getting reports of cryptojacking attacks inside major HPC centers in the UK, while in Germany, where it was publicized. However, I'm sure others on this call know of other cryptojacking attacks that occurred in infrastructures closer to home. The University of California had a major ransomware attack on some of their HPC infrastructure, and they ended up paying a substantial amount of money to get medical research data back, vast amounts of data. In 23, the actual fragility of the data sets inside HPC was demonstrated by Google, where they were able to completely poison data sets with as little as a 0.1% change in the learning data sets, and it actually So if somebody can get access to your systems, then certainly the opportunity to create chaos with a small amount of data relative to your holdings is potentially there. 23, Azure has published substantial guidance on theft of service inside large HPC, large clusters, which would extend to their HPC as a service. And as early or as late as September of this year, you may be aware, and we'll go probably take a look at it, but NVIDIA had some substantial vulnerabilities that allowed container breakout inside their GPUs and compromised, basically allowed for one tenant to see the other tenant's data. In the interest of time, I'm not going to go through this, but to drive the point home a little bit more, if you look at some of the standard types of equipment that you'll have in an HPC cluster, and again, this tends to be a little different, more high performance than you'd see in just regular data center. Just in late 24, NVIDIA has announced all sorts of vulnerabilities, and this information is available as common vulnerabilities and exposures both through MITRE and through NIST. The marks are there, so you've got the link and you can follow them. Mellanox switches, of course, supporting InfiniBand as late as August, a very high vulnerability announced. Supermicro chassis. I didn't look at some of the other major OEMs, but certainly Supermicro is popular because of the value they reflect in a lot of RFPs. So they've had some BMC problems. Juniper also appearing in some of the infrastructures I see. Same thing. InfiniBand Fabric Manager, it's running on a ton of open source packages, and a number of those open source packages, in this case, an example is Cairo and HTTPD, have got some pretty serious vulnerabilities associated with them. And then finally, an area of recent work for me is in the area of data center infrastructure management. So this is the management network being used to manage the power distribution units, monitor heating, cooling, potentially the building management systems. So sort of the operational technology supporting the HPCI. And there too, there are vulnerabilities appearing in some of the open source packages. For some reason, all the links around OpenBCM didn't come out, but there were, I think, 3 vulnerabilities documented in the last 3 months related to this package. So there's a lot of ground to cover, and this is very contemporary, all of these issues. And so at this point, well, actually, I'll cover this and then I'm going to hand it off to Daksha. But the list, unfortunately, is fairly long when it comes to the vulnerabilities. Disruption of operations, and of course, if you're running large workloads and there's a failure, that is going to be a lot of lost time and expense. Corruption of data sets, we mentioned, is critical because that ultimately impacts the confidence in the scientific results or the analytics. In some cases, in the private sector, there could be financial data, personal data at stake. Theft of service, we've already mentioned. Multi-tenancy and side channel attacks, for instance, the GPU vulnerabilities from NVIDIA. The weak supply chain has to do with the fact that in some cases, particularly if you're using superpods or something like that, you've got a single, you don't have alternatives, right? You build it the way it's, you buy it from the vendor and you scale it that way. And if a vulnerability appears in any one of those components, then it's going to cascade throughout your infrastructure. It's not like you've got a mixture of vendors in there. Open source software, I think we all know about that. And DCIM, OT security, that's certainly one that's on my radar. Seems to be a bit of the soft underbelly inside the data centers, and of course, supporting the HPCI. One of the things you're going to hear us talk a lot about through this is NIST 800-223, which is the security for high performance computing that came out in February of this year as of version 1. And, they talk about zone specific threats, many of which we have covered here. And they, you'll see here, they even talk about the data center infrastructure as well. So the discussion you're going to see is not only framed by 800-223, but it's also well aligned and probably goes beyond what 800.223 was talking about in terms of threat and risk management. So now I'd like to hand it over to Daksha to take you through Zero Trust and give you an understanding. And Daksha, you just let me know when you want me to flip the slides.
Thanks, Tyson. So all of the threats and vulnerabilities that Tyson just discussed is one of the reasons we are talking about Zero Trust with respect to high performance computing. And that is the cybersecurity landscape is evolving and morphing like we've never seen before. And Microsoft recently released its Digital Defense Report for 2024, probably the past month. And one of the key insights noted here is that in 2024, the education and research sector became the second most targeted sector by nation-state attackers. Now think about that in context to HPC and research, right? And nation-states are some of the most resource sophisticated threat actors. And as you can see in the chart, the IT sector is the most targeted at 24%, and followed by education and research at 21%. And those numbers are pretty close. And then you have the government at 12% and think tanks at 5%. So you're hitting over 50% of the attack sectors there. And just like everybody else is doing research, the threat actors are doing their diligence, doing their homework on their attack options, conducting analysis and research, leveraging high-performance computing to test and validate, and then conducting actual attacks. It's sort of fascinating. So let's go to the next slide. So one of the other reasons we're talking about Zero Trust is the prevailing mandates and legislation. Zero Trust as a concept has been around for a while, starting back in 2004 when the Jericho Forum brought forth the discussions on deperimeterization. And then it was followed by Forrester's John Kinderwag in 2009, where the term Zero Trust got introduced into industry. In 2014, Google adopted the BeyondCorp model of Zero Trust and then released a series of papers based on those implementations. And then in 2018, NIST now published the Zero Trust architecture. It was the first draft that came out, which provided detailed guidance on designing and implementing Zero Trust. So in May 2021, now all this timeline starts to implicate what we're doing right now, right? So in May 2021, the US executive order that directly mandated federal agencies to implement Zero Trust principles to strengthen the nation's cybersecurity defenses was issued. And this order focuses on transitioning the government to Zero Trust architectures to protect the nation's critical infrastructure from evolving cyber threats. And then in 2022, the OMB issued the Zero Trust strategy, requiring agencies to meet specific Zero Trust architecture milestones by the end of 2024, which is where we're right now. And in 2023, to support this, the executive order and the other mandates, CISA issued the Zero Trust maturity model as a framework to guide the transition towards Zero Trust. So it's much more concrete in terms of prescriptive transition plans and steps to progress through. And then earlier this year, in February 2024, NIST released its HPC security standards under 800.223 that we just discussed as well. But the standard does not directly talk to the previously set forth Zero Trust mandates. And then around the world, Zero Trust is obviously taking hold in the European Union. You see it under the DORA Act, under NIST 2, and in the UK, it is embedded in the government cybersecurity strategy, the 2022 to 2030 direction. So so I guess here we're in an era where the nation's critical infrastructure has mandates to implement Zero Trust. So Tyson, can we move forward to the next slide, please? Thank you. So let's talk a little about what is Zero Trust. We want to do a little bit of a level set because there's a lot of information out there. So Zero Trust is not a product or a service. Zero Trust is a way of thinking. It is about minimizing the attack surface as much as possible, giving users or a device or an entity in an environment only access to exactly what it needs, like as you can see in the figure. So instead of using a full VPN into your environment, which if you did use a VPN, you have full access into your entire infrastructure. So Zero Trust is about compartmentalizing the data, segmenting the data, compartmentalizing how information is accessed as relates to the specific roles and responsibilities of the user that is coming into the environment. So that's authentication, authorization, microsegmentation, and managing those makes a big difference in minimizing these attacks. So a breach of an individual user or device should not lead to the breach of an entire environment or an entire organization. You want to think about the general lay of the land architectures of HPCI as well in context, right? So Zero Trust is predominantly based on the three fundamental principles, the core being never trust, always verify. So not just verify, but authenticate and authorize, and then use other data points surrounding like device health, data classification, anomalies to have context. The second principle being the principle of least privilege, limit the user's access with just-in-time access, just enough access, and other risk-based contextual information to protect the data and assets, and assume breach. It's about microsegmentation, reducing the blast radius, encrypting traffic, using threat detection, and assuming that the adversary is already in the environment. So let's go to the next slide. So according to NIST, in the standard, Zero Trust approach is primarily focused on data and service protection, but it can and should be expanded to all enterprise assets, which includes the devices, infrastructure components, virtual cloud components, and the subjects here, which are shown, which are the end users, applications, both human, non-human. And there's a control and a logic between the subject accessing a resource. So this diagram is a logical depiction of the different components seen in the NIST Zero Trust deployment for the enterprise. And any of these components, they can be distributed. They can be operated on premises on a service, or they could be operated through cloud-based services. And this is literally just a logical depiction. So on the top, you see the policy decision point. And this is where there's information ingested from all those data points that you see on both sides from the different arrows, like the CDM system, which is the continuous diagnostic and monitoring, and then threat intelligence. And so based on all the ingestion of these data points, the policy decision point makes a decision to authenticate or authorize or provide access to a resource. And this is essentially enforced below there through the policy enforcement point to either provide access or terminate, or even terminate at a certain point in time, right? So, so NIST also says that once a security posture is established for the assets, when they move between enterprise and non-enterprise infrastructures, the security posture and the policy should be maintained consistent between on-prem and off-prem, right? So that stays. And it also encompasses devices as they move around the environment, on the enterprise network, off the enterprise network, including workloads that might be on enterprise environments and then onto non-enterprise cloud environments. So basically, it is an entire end-to-end framework. So let's go to the next slide. So this slide is more of a more of a tangible depiction of that logical context. So all this to say that Zero Trust is like a holistic approach that extends the entire digital estate. So it includes, and you can see them highlighted here, identities, endpoints, network, data, applications, and infrastructure, right? And Zero Trust serves as a comprehensive end-to-end strategy and requires integration across all of those elements. And we're going to see those 5 elements as pillars in the Zero Trust maturity model that we will talk about shortly. The intent of this, again, is to capture all, can you just go back a little bit?
Sorry. Yeah.
Is really just to point out, like, the inclusivity of human, non-human identities are on the right, serverless or containers. So again, this diagram, just to give you a feel for a tangible feel for the scope and span of what was addressed under NIST for Zero Trust architectures. So let's go to the next slide now. And I do want to bring your attention here to a quick summary of what Zero Trust is and what it is not, seeing as there's a lot of information out there. Zero Trust is not a product or a service. It's not a solution that you can purchase off the shelf and say, hey, I implemented Zero Trust. It's not a one and done. It's something that requires ongoing refinement. It is iterative. It spans multi-years. It's not security awareness training or certifications. And also, it's not even a pre-templated set of security controls that you could just take and apply. So there's a lot of thought process to this. It's a way of thinking. So instead, Zero Trust is a paradigm shift. It involves the processes, procedures, technology, people, and adoption of a Zero Trust culture on top, right? It's very, very rarely a rip and replace scenario. So people with legacy infrastructure, it's not to be to discourage. It's not a rip and replace. It's about integrating with the technology strategy of the company or the organization, and it's aligned with the risk appetite and the posture, right? So this would again weigh on what is happening in the overall bigger context of the environment. And of course, Zero Trust does not solve it all. It works hand in hand with defense in depth and DevSecOps and security incident response and all the other security goodness that we have today in our environments. So essentially, Zero Trust is not about being 100% secure. It builds resiliency in the systems, and it shifts the paradigm from how we used to architect before in the castle and moat model to designing from inside out. And here on the right, you see CISA's Zero Trust maturity model. It shows the 5 pillars that we just talked about. And the journey is shown in the left there, where the work is to be done from moving from traditional upwards through initial, advanced, and optimal. And it is a multi-year journey through different pillars, and you don't move through all the pillars simultaneously as well. There's a lot of interdependencies to consider as you progress through the Zero Trust implementation process as well. So let me turn it back to you, Tyson.
All right. Thanks, Daksha. We've got about 15 minutes left, so pace is going to continue to be quick. I know we're moving fast, but fortunately, this is also all documented. So if you look at the NIST guideline that we keep talking about, 800-223, it is a discussion of HPC security and some of the threats. And really, it's starting to provide guidance in the US. And you might ask, well, why are we focusing so much on the US and their guidance? Well, one reason is because that is probably where most of and the best guidance is coming from. And here in Canada, we, as I said, we've got some gaps. However, there's a lot of pressure building. We talked about the critical infrastructure designations. So it's highly likely that whatever Canada does will be closely aligned to what we're talking about here and now today. And in the case of NIST, it does not really speak to Zero Trust in any way. And we came to this topic because in participating in the drafting of 800-223, they started asking questions about how does this work with Zero Trust? So Daksha and I put our heads together and came up with this effort here. If you haven't read 800-223, this in a nutshell is the reference diagram for HPC, where they have a high performance computing zone, which would be where you've got your GPUs and your DIMMs, your storage area network, your high performance network, which is likely going to be either RDMA or RoCE, so InfiniBand or some type of high performance Ethernet. You've got the access zone, which would be where the researchers or workers or scientists would log in, potentially transfer in their data to the storage zone, so as a hop. And then we've got the management zone where you'd have your orchestration and management features, functions, your schedulers, your slurms, etc. in this network, all connected by a back-end regular commodity Ethernet. All right, so yeah, we already talked about some of their recommendations. I'm going to move past this fairly quickly, but you see they do prescient, they're already talking about container security when they published the document in February, and then lo and behold, a major container security issue arose in September of this year. Now, this is very applied, what I'm going to talk about now. So ultimately, the conclusion that we came to, just to skip to the end, is that the first level of maturity, which is called traditional, is likely the one where most HPC clusters and managers will find themselves today. And as we go through each of the pillars, you're going to see that there's different types of opportunity to get higher in the maturity stack, depending on the pillar, and sometimes even depending on the zone that the pillar is considering. So you remember there's those 4 zones. Another point that Daksha made that's really important is that zero trust is not about a specific set of controls that have to be implemented. It's about understanding what makes sense in the context of your environment, trying to apply as many of the zero trust controls as you can. But also, given that there's 3 ways to manage risk: you can treat it, transfer it, or you can accept it. And accepting risk is something, the executives would be empowered to do based on guidance you get from people in this audience, for instance, about the cost, complexity, or performance impact of these controls. And by the way, cost, complexity, and performance impact were the 3 criteria that we considered when trying to determine whether or not a control was viable. So now some examples. So identity was the first pillar. And some example identity controls, this could be things like, standard username, password, provisioning, different types of provisioning and access technologies, like Kerberos, for instance. It could also be issuing digital identities through public key infrastructures or based on public key infrastructures. And it includes technologies like multi-factor access control, whether that's based on a mobile phone or some type of soft token. Going back to the old days, those old hardware RSA tokens, all of that was multi-factor and is really kind of the bread and butter of access control these days. And the conclusion that we came to through these interviews and processes was that for the identity pillar, it would be reasonable to expect that an HPC cluster could get up to the initial level of maturity. Based on conventional practice. That is to say that most of these clusters would have multi-factor access control for the researchers coming into the access zone, particularly. They're often using self-managed identity stores because at the higher levels of the maturity stack, you see they're looking for things like enterprise-wide integrity and integration. And of course, if you are one of the regional HPC clusters, it's unlikely you're going to have an LDAP directory that's got, that's fully integrated with the LDAP directories or ADs, Active Directories of all the other institutions who have got researchers coming in. That would get very complex very fast. But they're also expecting that there would be risk assessments being performed, although on a manual basis. As you move up the stack, you start to get into automated risk assessments. Why is somebody coming in at this time of day from this location? And then having controls on that. But, when we say it's possible, the yellow, generally it means that given additional resources in both people and probably money, funding, then you could probably implement these controls without impacting performance or complexity in unmanageable ways. And the red, the problematic, means that even given reasonable resources, it's still going to be a heavy lift and likely encounter a lot of friction in its deployment. The next pillar is devices. So devices could be both the servers sitting in the compute environment, the GPUs, all the way out to the laptops and the workstations used by the researchers. And in this case, some example of device-based security controls, host-based firewalls, application whitelisting on these devices, EDR, endpoint detection and response, command accounting, privilege access management. All of these tend to be either agent-based or potentially baked right into the operating system. So when you look at the feasibility of that, the conclusion we came to was that you can't consider all devices across the board. You look at it from the one class of device, which we called management, which were devices that are used, say, in the management zone or in the access zone or at the far edge where the researchers or the scientists are coming in from their workstations. And in this case, you can move fairly high up the stack, up to the advanced level, given sufficient funding and resources. So in other words, executive commitment. If you wanted to get to advanced for management devices, you probably could without impacting the core performance features and functions of your HPC cluster. But most people can reasonably be expected to be operating at the traditional level. So advanced is things like you're tracking your assets, both physical and virtual. You've got integrated threat protections. So this would be, like the host-based firewalls and or EDR functions, those sorts of things, but they require time and materials and resources to implement. The other device that we considered was the workload devices. So this would be storage and compute. And when we looked at it, and the feedback we got was really getting beyond the initial level of maturity for zero trust would be very problematic from a performance perspective. So for instance, if we go back here again and you look at advanced, getting enforced compliance and integrated threat protection, agent-based controls onto a storage system is probably just about impossible, unless you're using something open source and you've got some open source solutions. But the storage vendors don't generally allow you to install agents, and certainly you're not going to want to burn CPU or memory cycles on a server to host some type of agent. So different profiles for different devices in this pillar. The network was also another place where we had to split up the pillars. An example of different types of network controls, segmentation, inline firewalls, inline IDS, or it could be passive, hanging off a switch, various types of network access control. Encryption of data in motion is frequently spoken about, which is essentially encrypting the application communications across the network. And then finally, connection authentication, where every type of connection goes through some sort of handshake involving key exchanges. When we looked at the viability for network-based controls under the Zero Trust framework, again, there is a clear difference between devices, workload versus management networks. In the management network, which would really be the network on the back end that connects the management, the access, the compute, and the storage, given the resources, you could probably implement all the way up the stack in terms of the security controls, all the way up to things like micro segmentation and just-in-time dynamic access control, profile auditing. So in other words, if somebody's coming in and they're trying to run an application and this doesn't fit their predefined profile, then you do something about it. You remediate that. You could do that without necessarily compromising the integrity of the performance. And you could probably do it even with researchers coming in from all sorts of other types of institutions, but it would be expensive, just to be candid about it. In the case of the network controls, are recommended in Zero Trust for the workload networks. So, Rocky or InfiniBand, very difficult to implement the recommended Zero Trust controls without having some pretty serious performance impacts. So I think if we look at advanced, you see encrypts application traffic and manages issuance and rotation of keys. So could you imagine trying to nail up a TLS session every time one set of GPUs in one server wanted to speak to another one for some type of collective operation, encapsulating MPI inside of TLS? Even if you could accept the hit as far as performance is concerned, because of all the load on the CPU. In fact, I don't even know if RDMA would necessarily work with TLS very well, because RDMA is about kernel bypass, and I'm not sure how you do kernel bypass with TLS. NVIDIA does have a solution related to network encryption, which I'll talk about very briefly, but it seems that even if you could afford it, the complexity of it would itself generate a lot of risk. Applications and workloads is the fourth pillar. Some tools here: code scanning, orchestration and management of security capabilities, development and testing, the use of trusted execution environments. So these would be essentially compartments off to the side of the CPU with secured memory for running applications and storing keys. All of these things are available in the market as off-the-shelf products, but implementing them inside an HPC environment, what we were told is that in many cases, the expense would be very significant, but also when you got to the higher levels of maturity, trying to enforce the level of discipline around SecDevOps on experimental applications and or a diverse user community would probably result in rebellion, I think was a word that was used. And ultimately, while the traditional level of maturity should be probably a baseline for an HPC cluster, the initial level would be achievable, which would be to having some type of workflow, that was understood and agreed to, formal code deployment mechanisms. So, for instance, perhaps having code scanned prior, for vulnerabilities prior to deployment through a common utility, maybe made available in the access zone. And the same thing with static and dynamic testing prior to deployment, possibly tools, if budgets and deployment resources exist, could be provided in the access zone to get to initial. Beyond that, the friction would really start to make it so that executives would probably be able to, say we accept the risk relative to the cost and complexity. So the last one is the data pillar, which would really represent the storage domain. And of course, some of these features are baked in already to the products: encryption, inventory systems, backup and recovery. So a lot of this is part and parcel of many of the solutions, but some of it, like data loss prevention, where you're trying to understand and track metadata and sources and destinations, may prove to be again, beyond the capabilities and at the point where the decision is made to accept the risk. So in this case, what we're looking at is that probably getting up to the initial level of maturity, given the native functionality of a lot of the storage tools that are in place already, should be possible. There's some type of inventory available. Perhaps not very granular, but you have an awareness of what's being stored, how it's categorized, high availability. Of course, there's all sorts of redundancy built into these arrays already, and they manage their own encryption keys or they'll allow you to manage it. So that will get you to initial, which seems like a reasonable target. And also included throughout this, and you saw it when Daksha showed you the 5 pillars, there are these horizontals of visibility, automation, and governance, which are really would be features and functions associated with whichever products you chose that could then be brought together into a dashboard. But ultimately, if you look at what we've just walked through, and you've got your 5 pillars: identity, device, network, apps and workload, and data, you can see that the different pillars offer different opportunities for higher or lower levels of maturity, balancing cost, complexity, and performance impacts. And this is sort of the granular view of it. But if you were to look at it holistically, and to go back to the beginning, traditional seems to be the absolute baseline that should be achievable. And the initial level would reflect a reasonable balance of cost, complexity, and performance risk. and would be subject to budget, budget and resourcing. And if you start to get designations as being critical infrastructure, then likely the initial level of maturity would be the appropriate one, given that ultimately these clusters are tuned for performance and to get jobs done. So finally, and this is the last slide, if you were to sort of try and overlay what we've just communicated on top of the reference design from NIST, you'd sort of see that in the performance networks, the best you're likely to see is traditional maturity, because it becomes very difficult to implement key management or encryption in that network. I said I'd mention some products. NVIDIA does have some options in the InfiniBand product line for attempting to monitor traffic inside an IB network and even encrypt it using their Bluefield DPUs. I would mention, though, that according to the research that I've done, the encryption is actually IPsec. So you would have to be running either Ethernet with IP, and then I guess Rocky on top of that, or it would seem rather absurd to run IP over IB and then potentially try and run IPsec. I'm not even sure if that will work, frankly, but there are solutions out there. I don't know how well they're selling. Certainly the Bluefield DPUs have got some cost considerations associated with them. When you get into the data storage, the compute and the storage clusters themselves, initial maturity seems like, again, going to be a reasonable target. It's when you get out onto the right-hand side, you're getting in the access zone and the management zone, where advanced maturity becomes something that can probably be targeted given the reasonable resourcing. And then in the management network itself, which joins it all together, there's certainly an opportunity to get towards optimal maturity in that management network, which, considering its important role in acting as essentially the bridge and the interface between the zones, would be a reasonable place to concentrate effort to try to get to higher maturity levels for an HPC cluster. And with 4 minutes to spare, I'd like to thank you for your attention. And as I said, we've gone through 65-page white paper in the course of about 40 minutes or less at this point. But Ralph, if there's any questions, I think this would be, we'd be happy to take whatever we could in the time remaining.
Thank you so much. That's as I expected. It was a great session and very beneficial to me, and I'm sure that other attendees enjoyed it.
And of course, please, if you have comments on the paper itself, it's open science, it's in the public domain. Feel free to share it. If you direct people back to the Carleton site, at least we'll get a little bit of insight into how many people are accessing the paper, which is always helpful too.
Thank you again, and thank you all the attendees for joining us today. We appreciate your interest for securing our digital environment. We would love to hear from you. Please feel free to connect with us through Slack or the email, as you can see at the bottom of the screen. Give us your feedback, and if you have an additional question for our speakers, we will be happy to hear from you. Our next session will be DRI-wide cybersecurity training panel on October 29th at 1 p.m. Eastern Time, where we will discuss effective strategies for cybersecurity training within the DRI ecosystem. So thank you again, Tyson. And Daksha, that was a fantastic presentation.
Thank you for having us again. Thank you.
And thanks everyone, and have a great day.